All right. The first part of what we're going to finish today in chapter 15 is drawing without replacement. You guys have done this before. It's not new. I'm just going to remind you that it happens. So in chapter 14, some of you guys are asking me questions like, well, we're taking one out, so don't we need to reduce the number that were there? But when you have super large groups, you know, like tens of thousands of M&Ms or whatever, it doesn't really matter because the result is insignificant when you start taking one out. But if you're dealing with cards or something with a very finite group of people, then you definitely need to start subtracting out because the probabilities would definitely change. Okay? So, here's a cards example. You're dealt a hand of 3 cards, one at a time. Find the probability of each of the following. So in this case, you have 3 cards, so you're going to be multiplying. So the first one says the first heart you get is the 3rd card dealt. That means you didn't get a heart, and you didn't get another heart, and then you got a heart. So, how many cards are not hearts? How many cards are not hearts?
Oh, this is probably one.
There's 39 cards.
I thought it was just the 3 cards.
Okay, I understand. I get you. So there's 39 cards that are not hearts out of 52. I'm sorry. I'm sorry. All right, well, the next card, so we've taken a card out and we didn't put it back in. So the next card also is not a heart. So there's 38 not hearts left. And there's also only 51 cards left, not 52. Right? Because I took one out. Now I've taken 2 out. There's only 50 cards left. But this time I want a heart, because the heart is the 3rd card you're dealt. So how many hearts are left? 13. So then you just multiply all these together. And I did that earlier, and I'm not going to take the time to use my calculator. It would take me 5 minutes. So you get 0.145. Just make sure you're thinking about what you have and what you've taken out. So I'll talk through B and C, and then we'll do D. On B, your cards are all red. So how many red cards are there? 26. So you'd have 26 out of 52, and then 25 out of 51, and then 24 out of 50. And you multiply all those together. Yeah? On C, the probability no spades. So again, there's 13 spades. So there's 39 cards that aren't spades. So you do 39 out of 52 times 38 out of 51 times 37 out of 50. Right? No big deal. On the last one, you have at least one ace. So we talked about that the probability of at least one something means we should do the complement. So this is the same thing as 1 minus the probability of no aces. All right, so how many aces are there in the deck? 4. So how many cards are not aces? 48. So we have 1 minus 48 out of 52 times 47 out of 51 times 46 out of 50. And you want to make sure you multiply all those together before you subtract from 1. Questions about that? You end up getting 0.217. Questions?
The only thing that was holding your slide down.
Any other questions about this problem?
No.
Okay. So again, if you have a finite number of things and you're drawing and you're taking this out and not replacing them, make sure you're keeping that in mind when you're doing the problem. Not all of the homework problems tonight involve everything we've talked about today. Do not make them harder than they have to be. I'm just showing you a variety of methods that you could use to solve the ones for the assignment. We talked a bit about tables last week. So you had counts in the tables or you had probability in the tables. But then sometimes you don't have a table and you could use a table to solve the question, like to answer the question. All right, that's again another method you could use. So it says, for instance, in the drunk driving example in the book, we were told that 78% of suspect drivers get a breathalyzer test, 36% get a blood test, and 22% get both. And that's enough information to start a table, because maybe they start asking you then conditional questions and you don't have the information to do conditional questions. If they ask you just questions like we do with the Venn diagrams, you'd have enough information to do that. But then if they start asking you conditional questions like we talked about on Friday, then you need the other probabilities. So all I did was create a table. They said that 78% of the drivers got a breathalyzer test, so that's total. 36% got a blood test, so that was total. And 22% got both. And we know the table percentages have to add up to be 1, right, 100%. So I could go back through and I could use the information that I have to fill in all the other pieces if I needed to. Like I could fill in 0.22. I could do that. If I wanted to know the probability that they don't get a breathalyzer test, sorry, get a blood test, get a breathalyzer test right here, I just do minus 0.22. So I have enough information that I could go back through and create a table if I needed to. I could find all of the missing pieces to answer any of those questions. Does that make sense? So we're going to just to make sure I've shown you how to do it. After surveying 995 adults, 81.5% of whom were over 30, the National Sleep Foundation reported that 6.8% of all adults snored. 32% of the respondents were snorers over the age of 30. Right? We have age, and we have snoring or not, right? So we have people that are under 30, and you have people that are over 30, their age is under 30 or over 30. And then we have people that snore and people that don't snore. Again, I know this table should add up to be 100%, so I know that much. We're just going to go through and fill in what we had. It said 81%, 81.5% were over 30. And 36.8% snored. And 32% of respondents were snorers over the age of 30. So I could fill in all that information. Then I could use that to my advantage to answer the question. So the question says, what percent of the respondents were under 30 and did not? So under 30 and did not snore is this box right here. Right? Maybe? Okay. So I have to do a little bit of work to get an answer, but it's not going to be that bad. 81.5% were over 30, 36.8 snored, 30% snores over the age of 30, so we can figure out some stuff. For example, we need to know, this is one way to get there. We could figure out the percent that were under 30 and snore. So how could I find that number? Yeah. 0.368 minus 0.32. So we get 0.048. Right, it's pretty much just 368 minus 320, right? Yeah, 48. Questions about that? Where I got that number? We could figure out this number down here, the total percent that were under 30. Again, we could do 1 minus 0.815. So what's 1 minus 0.815? 0.185. And so then I could go back and I could figure out what's missing. So I could do 0.185. I did it earlier, but that's okay. 185 minus 0.048, 0.137. So that would be the answer to part A. That was one way to get that answer. Do you have to do it that way? No. Just one way to do it. All right. Questions about that? Now, part B says, is snoring independent of age? That gets a little bit tricky. Some incidences, it's easy for you to say if something's independent or not. You know if one outcome is going to be related to the other. Some you don't know. You're not sure. So I have a definition I can give you. Just make sure you know every single time if it's independent or not. All right. So we're going to come back to this question. You need to make sure you know when things are independent. Again, independent means one outcome doesn't influence the other outcomes. You have this formula right here that tells you if something is independent or not. It's not on the AP formula sheet. So if you're going to use it, you have to know that one. So if you have the probability of B given A, it needs to be the same as just the probability of B occurring by itself. Then they're independent. So I can do an example, and I can do the question we just skipped over. So last week we talked about the college students living on campus and the meal plans and yada yada. So it says, our survey told us that 56% of college students live on campus, 62% of a campus meal program, and 40% do both. Are living on campus and having a meal plan independent, or are they disjoint? You should be able to answer this question right now. What does disjoint mean? Right, there are no outcomes in common. Can a person have a meal plan and live on campus? Yes, so then they are not disjoint. Right? All right, so then let's do the probability of living on campus given they have a meal plan. I think we did that one last week. If you use the formula, then you do the probability of both over the probability of what's given. So what's the probability that you are living on campus and you have a meal plan? Probability of living on campus and having a meal plan. 42. Now you divide that by the probability of what's given. It's the probability of a meal plan. So what's the probability of a meal plan? 0.62. So then 0.42 divided by 0.62 is 0.677, because I did it earlier. So I did the probability of B given A. They're going to be independent if that number equals the probability of just B. So in this case, probability of B is just living on campus. So does all of this, which was 0.677, equal the probability of living on campus? What's the probability of living on campus? 56. Are those equal? So they're not independent. All right, so the math shows that it's not independent. You don't have to like figure it out and like think it through or anything. You know it's not independent. They're not independent events. One outcome may influence the other. That should make sense. A lot of universities, if you live on campus, they force you to have a meal plan, right? So those would influence each other. Questions about that? Let's go back to this snoring question then. It says, is snoring independent of age? So I did it. Probability of, I did snoring given they're over 30. So if that's B given A, I need to make sure it's equal to the probability of just snoring. So what's the probability just of snoring, just in general? Right. This is the probability of just snoring. And the other one to go through and actually do the formula. So what's the probability of snoring and being over 30? And then divided by the probability of what's given, that's over 30. So what is that probability that both of those occur? Snoring and over 30. 0.32. And what's the probability that you're over 30? And so I did that. I'm trying to see if this is equal to 0.368. I did this earlier. That's 0.393. Close, but are they equal? No. So they're not independent events. All right. Again, that should make more sense too. Generally, not always, but generally, as you age, there are more health problems that could lead to snoring. So more people over 30 are going to snore than younger people. Okay, so it's not always the case, but that it would show why they're not independent. Questions about using that formula? If you have the math, you don't have to think about it. Doesn't matter. Generally, you just want to assign it so that you can use what you have instead of having to go through and like recreate anything. So if they had already given me, if you'd already found some probability of something given something else, just use that. Or if they don't give you certain probabilities in the question, you don't have to find them. Use what you have to see if you can make, use the formula without having to figure something extra out. But it shouldn't matter. So if I did the probability of over 30, given they were snoring, then that should equal the probability that they were over 30. And that won't work either. So any other questions about the formula? All right. One more example of that. As the real estate ads described in exercise 1, 64% of homes for sale have garages, 21% have swimming pools, and 17% have both features. If a home for sale has a garage, so this is a conditional probability because it's giving you some condition you have to meet. What's the probability that it has a pool too? So I'm just looking for the probability of a pool given that there's a garage. So make sure you're reading into that. The clauses are important. They give you the conditions you have to meet. So if we use the formula, what's the probability of a pool and a garage? 17. And what's the probability of just garages? 64. And so I'm pretty sure this one earlier too. It just takes me a long time to write them in my calculator. Yeah, you get 0.266. All right, so that's the answer to part A. On part B, are having a garage and a pool independent events? Well, we have an equation for that too, and we just found a conditional probability, right? The test for independence says the probability of B given A has to equal the probability of B. Well, I just did a conditional probability, so maybe we'll just use that. If we're using that, then B is the probability of a pool, so what's the probability of having a pool? 0.21. So again, close, but not so much. So they're not independent of each other. And C, are having a garage and a pool mutually exclusive? What does mutually exclusive mean? What's another word for that? Disjoint. And so are they disjoint? They're not disjoint because you can have a house with a pool and a garage. Right? Disjoint means they have no outcomes in common. That would mean that the houses that had pools could not have a garage and vice versa. The pool is not the garage. No. All right, questions about that? All right, one more type of problem then. Tree diagrams. I love tree diagrams because generally you know when to use them. If there's a sequence of events or a sequence of if-then statements, like if this happens, then this happens, or if this happens, then this happens, then you know to use a tree diagram. The rest of the stuff we've talked about, it's like you got to figure out when you want to use it. A tree diagram is specifically designed for a sequence. All right, so I've got an example. Leah is flying from Boston to Denver with a connection to Chicago. The probability her first flight leaves on time is 15%. If the flight is on time, the probability that her luggage will make the connecting flight in Chicago is 95%. But if the first flight is delayed, the probability that the luggage will make it is only 65%. See, there's like a sequence of events. Like if it's on time, then this happens. If it's not on time, then this happens. All right, so that indicates to me I should use a tree diagram. So I'm going to go ahead and make the diagram that can go back and answer any of the questions. So you have Leah, who's flying from Boston to Denver. The first thing is the flight going to be on time, right? The luggage is dependent on if it's on time or not, correct? So we're figuring out if it's on time or not. So what percent of the time is the flight on time? And so then what percent of the time is it delayed or not on time? 0.85, right? Those have to add up to V1. Then it starts giving you these conditional things. So if the flight was on time, then the probability that her luggage will make the connecting flight in Chicago is 0.95. So luggage makes it. But so that means if it's 95% of the time it makes it, then that means 5% of the time it doesn't make it. Does that make sense? Then it said if the first flight is delayed, the probability that the luggage will make it is only 65%. Which means if the flight is delayed, then 35% of the time, the luggage doesn't make it. Well, it's an airport. What, are you shocked? I'm not. All right, now I can go through and I can answer specific questions. I can answer any question that says, what's the probability the luggage makes it given they're on time or given that it's delayed? This part is always going to be the given part. So I can answer conditional probabilities if that's what's given. All right. I can also go through and multiply any branches, like as a path. Like I can go from here to here and multiply those across, and I can get the probability of that happening. Once I do that, I can go through and I can start adding probabilities. If I want to know the probability that the luggage doesn't make it at all, there's two scenarios where that doesn't happen, so I can add those together. You can use a tree diagram to do a lot of things. So first of all, you don't need the formula for this. Are the first flight leaving on time and the luggage making the connection independent events? Are the outcomes related at all? Yes, like they are way dependent. The luggage making it is dependent on if the flight is on time, right? So those are not independent events at all. You do not have to do the math. You can. This one's very easy to explain, right? To a tree is a sequence of things. So one event is dependent on the other one, for sure. Okay? So B, what is the probability that her luggage arrives in Denver with her? Well, her luggage arrives in Denver if her flight was on time and her luggage makes it. And it also arrives in Denver on time if the flight was delayed and the luggage makes it, right? These two blank spaces would be the outcomes we need to add together, right? To get these blank spaces, we multiply across the tree. So we'd have 0.15 times 0.95, which is 0.1425, and 0.85 times 0.65, which is 0.5525. I'm staring at my notes, and it's printed from this page, and they're like microscopic. So the probability that her luggage arrives in Denver with her, I need to add those two together, and the probability is 0.695 or 45. I can't read that. 95. Does that make sense how I got that? I could also just answer singular questions, like what's the probability that her luggage makes it given her flight was on time? That would just be this number. What's the probability that her luggage makes it given it was delayed? That's just this number, right? Problem. If you the formula for those if you needed, if they were just one singular event. You could have done the same thing if it said, what is the probability that her luggage does not arrive in Denver with her? You would just add the other two outcomes, okay? So you can use a tree for a lot of things. What you cannot use a tree for is working backwards. For example, remember Leah? Because we just did this. Suppose you pick her up at the Denver airport and her luggage is not there. What is the probability that Leah's first flight was delayed? So now we're saying, given her luggage is not there, I wrote that backwards. They're giving you a condition. The luggage is not there. So that's the given part. Right? That's your conditional part. Well, if the end of the tree, remember this part at the very beginning is the given part. So now it's backwards. So I cannot work backwards along the tree. I can't start going opposite. All right, I can't start at the end and go towards the beginning. So for this one, I'm going to have to use the formula, the conditional probability formula. But I can still use the tree to get the numbers. I just can't actually multiply across the tree to get the answer. So what's the probability that the luggage is not there and it's delayed? Both of those happening. Well, that would be this path or this branch, which is 0.2975. That's the probability of both of those happening. When we divide by what's given, what's the probability that the luggage is not there? Well, the luggage is not there here or here. So we need to add those together in the denominator. Bless you. If you do that, you get 0.9754. So in this case, again, they gave you a condition from if you would be working opposite of what you had in the tree. So you could still use the numbers from the tree, but you'd have to work backwards and use the formula.